record it. Yeah. Tell me in the first line, which line? Here. No, we want to prove this. So I'm still writing it. I haven't written anything. Which line? This line?
Yeah, the inequality should be reversed, right?
No. This is what we want to prove. The other way is true. Oh, see, wait. Yeah, inequality should be reversed. That's right. Correct. You are right. That's what we want to prove. So, yeah, that's right. Right. This is what we want to do. So you are right. So this will be like this. Yeah, that's what I'm writing. Okay. Oh, but it's not coming there. It hasn't got changed there. Ah, it's changing. I'm sorry about this. Yeah. Yes, it's working. So no problem. Okay. Yeah. So you are right. Thanks. So the inequality should be this way, and that's what we want to prove. Correct. So the other way is true, of course. Correct. So this is what we want to prove. So to prove that, I take this. Okay, I take that, and that is. So this is the subadditivity. So that's what we have. In infinity, mu star of E intersection Sn. Right? Is that Sn? That's right. Oh no, sorry. Why did I write Sn? This I can write it as An. Okay. It's fine. Oh, it's gone again. Oh, it's there. Okay. Okay. Plus mu star of. I haven't done anything. I have just used the subadditivity property. Okay. Ans are disjoint. So I'm just using subadditivity and I've written that. I've used subadditivity to prove that this is less than or equal to this. Okay. Nothing. It's clear, no? This is less than or equal to. I have underlined two things, and that is less than or equal to that. The other term, I am keeping it as it is. Okay. I'm just using subadditivity of mu star. Okay. Then this is by just light it in a limit n tends to infinity, summation n equal to 1 to maybe capital A. Okay. N equal to 1 to n. Okay. Is that okay? Plus mu star of intersection S count. Okay. So let's keep the n as it is, n tend to infinity. But then we have assumed ans are disjoint and mu star is finitely additive, okay, which is equal to mu star of E intersection Sn, okay, plus mu star of E. I'm keeping the other term as it is, okay, since mu star is finitely additive, which we have proved already. Okay, is that fine?
Yes, this is fine.
This is fine. So because of that, okay. Okay. So this is yes, and that's n complement. Okay. Okay. But then then Sn is contained in S. Okay, so this implies mu star of Sn is contained in mu star of S. We have initially noticed that it's what is called monotone. Okay, because of that. Okay, we have noticed that it's monotone. So because of that, this is always true, right? So this thing is less than or equal to mu star of. There is no n here. E intersection S plus mu star of E intersection S. Okay, it's fine. Right? Is it okay?
Sir,
We took the limit outside,
sir,
then use the monotone property to prove this. That's all. I'm not able to see the video.
sir, yes,
So there it's
sir,
recording and
is yes,
yeah, say it again.
sir, is yes a monotone sequence or a disjoint sequence? First, we assumed it's
ANs are
disjoint. It
disjoint.
can't be both,
No,
right?
no, ANs are disjoint. Sn is increasing. ANs are disjoint.
Okay.
Sn I have defined to be your union of n equal to 1 to capital N of AN. ANs
Okay.
are SNs are not disjoint. I'm using the additive property of AN here. Additive property of mu n here. Okay, here.
Okay, sir.
Okay. So SNs are increasing.
Yes, sir.
ANs are disjoint. Okay. Then I use the monotone property. It's just you take the limit outside and then see that it's true. I mean, you can use the monotone property to prove this because we only want the inequality. We really do. We have proved subadditivity, so we only want the inequality.
Yes, sir.
So
Yes.
we
Hmm.
so we are starting with mu star of E intersection S plus mu star of E intersection S complement,
Correct.
right?
Yeah.
And then
Then
by
we
this
started with the intersection, yes. Okay. Then we took the limit outside because it's disjoint. We can write it as a sum like this, and we took the limit outside. Okay. Then we use the finite additivity of this to get the s inside. We took the we took using the s. We took the union outside, and we write it as a limit something. Then using the finite additivity, we can again take it inside. Okay. So it's equality here. Right? We get the SN here. Okay, sure. I'm showing something, but you want, then I have to write it. Okay. See, we started with intersection union something. This is our yes. Okay, this is our yes. Okay. Then we took using subadditivity, we took the union outside a summation here. Okay. Then we keep the n and we write the limit like this. But since this is a finite sum, you can take the sum inside as union. Okay. Then we get the Sn here. Since this is this union of An, which is Sn. I have written it here. Okay, this An is here. The sum of An, union of An, which is Sn. Now this Sn is contained in S. Now we have the monotone property. Using the monotone property, I get the greater than, less than or equal to inequality. Then there is no n. So the limit is useless. There is no meaning for the limit. Okay. There is no n. It's just a constant. Okay. So we got the inequality. Is there a problem? Is it clear?
Sir, at the end, we should show that it's less than or equal to mu star of E, right? But
No, mu star of E intersection. No, no, no. We started with mu star of, mu star of E we want to show. Correct, correct. But what did we get? We got that that is equal to this.
so I think we started and
Wait,
ended with
wait,
the
sorry,
same
sorry,
thing.
sorry, sorry. Right, right, right. That's right, that's right. So what did we do? We started with mu star of this. Okay. Oh, right. We started with that. We got back to that. No, that is just.
Yes, yes.
So we have to get E. Okay, that's right. Mm. I'm doing something wrong. Yes. So maybe I will erase this and come back again. Very good. I'm sorry. Thank you for that. Who was talking some time back?
Sir, Sayantan.
Sayantan. Okay. Very good. So let us go back from here. I want to use monotone properly. So how to use it? So that will go take me back. Since mu star is finitely additive, so I got this. Okay. So now, so limit n tends to infinity. Okay. So this is okay. So I keep it like this: mu star of E intersection Sn. Okay. Now this is now S complement is contained in Sn complement, right? So this is because of that mu star of E intersection Sn complement. Okay, this is okay. 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 This is fine.
Yes,
Now,
sir.
now Sn is in. Now Sn is in N. Okay. So this is equal to limit n going to infinity mu star E. Just mu star E. Okay, thank you. Now it's okay. It's fine.
And now it's fine.
Now it's fine. Okay, very good. Okay. Yeah. So yeah, I got carried away. And I got back to the original equation. Okay. So it is just the other one which is contained in there. So then from that it follows. Okay. It's good. So now what is that left? We have proved it's additive. We have proved it's a sigma additive and we have proved it's additive. Now we have to prove that it's actually sigma additive. The fourth one. What's the time? Oh, I have taken. Okay, I have 1 more minute. So before that I will do. So mu star is sigma additive 1 mu. And that is just clear because mu star is additive plus subadditive implies mu star is sigma additive. So if you remember in the very first class, we proved this. We just observed this. Okay. If you have an additive function, if it is subadditive, that's right, no? If you have an additive function, if it is subadditive, then it is right. Is that what I mean, the notes I sent?
Yes, sir.
Yeah. So we have to prove, yeah, if it is additive function and if it is subadditive, yeah, because additive D and using monotone, we prove the other inequality. Okay, that is the other inequality is just monotonous because the increasing union is contained in that. So because of that, you can take the limits. Okay, in the very first class, I proved that. And we just observed it. So using additivity and subadditivity, we get sigma additivity on the sigma algebra. Okay, so because of that, this is true. The screen is gone. Yeah, so we have proved everything. So we have proved that mu star is sigma additive on the sigma algebra mu. That's what we want to prove. From that we got our, so now the sigma A is contained in mu, and we have, so this mu can be bigger than sigma A. I mean, that will be the case. That will be the case most of the time, because of a property called completeness. You will see in the next class. Because mu will be complete. It will have all sets of, if you have any set A which mu star A is 0, then that A will be there in that set. So because of that, mu is complete. That's what completeness, which I have defined, which is defined in the very first class or second class. Okay? There is something called completeness of a sigma algebra. So I will define it again in the next class. And because of that, then this, if you take the Borel sigma algebra, so let's consider this. So one thing I want to, so if let x equal to r, okay, and a equal to finite union of n equal to k equal to 1 to n, ai, bi. Okay. One side open, it's open in the right and closed in the left. In R. So this is an algebra, okay, and define lambda of any interval AB equal to B minus A, or B greater than or equal to A. Okay. And then you can, by addition, you can define it on the sum, and that will be sigma additive on this, and you get the, what is called a Lebesgue measure. This lambda is called a Lebesgue measure. I mean, what I haven't proved it. Okay, I'm just Lebesgue measure. Okay, so I would like one of you to present the proof of this, which is there in any standard book. You can look at the book by Shiva Atreya and Sundar, where this is proved. So you can tell me either by chat now or through mail. Whoever sends the first mail, I will ask them to do, or you can discuss it. I mean, you send it in the group. Okay, we can discuss it, and one of you present this. So you can define this lambda on this algebra of half open, half closed interval, where we have to prove that it's sigma additive. By this, you have to prove it's sigma additive on this algebra. Then by this theorem, it extends to a sigma algebra. I mean, extends to the Borel sigma algebra. Borel sigma algebra is the sigma algebra generated by open sets. Here, open sets are generated by open intervals. Okay. So it's a sigma algebra generated by open interval or closed interval, because the property of the sigma algebra is the same sigma algebra, whether it is open interval, sigma half closed, half open interval, all those things are same. Anyway, we'll discuss it in the next class. So you tell me who wants to present this. Okay, it's a very elementary proof. It's not very difficult. It's just inequalities involving real numbers. Okay, so one of you tell me who wants to do that, and in Tuesday we will discuss this. One of you present this. Okay, I will anyway write a mail regarding that. Okay, any other question? So if there is no question, I will end it. Okay, bye.
Thank you, sir.
Okay, thanks. Bye.